Good morning, students. So, in today's class, we will be dealing with what we call an autotransformer. So far we have studied the in and out of a practical single phase transformer, and we will see how it is different from an autotransformer and why we need something called an autotransformer when we already have a transformer, how they are different. Okay. So the catch point is like in an auto transformer, part of the winding is common to both primary and secondary. You see, in an auto transformer, so you know that in a transformer, like what we have studied, a single phase transformer. So in a single phase transformer, you know that there will be a primary winding and a secondary winding. So, but what happens in an auto transformer is like a part of the winding, it will be both common to primary and secondary. I will show you the figure. So I will show you the figure. So this is the figure of an auto transformer. We can see that a part of the winding is both common to primary as well as secondary. See, so this is the source. So this will be the primary, and the secondary will be both combined. Will be the secondary. We'll see. You will understand it when we go deep into it. So here the transfer of the power can happen by both conduction and induction. In case of a transformer, the transfer of the power was only by using induction. You know, there was self-induced EMF and mutual induced EMF. Such concepts you have studied already. But in an auto transformer, the transfer of the power can happen both by conduction and induction. So what happened? As a result, since both the phenomena are involved, the power will go on enhancing. So we will get the power due to conduction as well as we will get the power due to induction. Okay. So before we move into the induction effect, we will see how a resistance potential divider works, because you need this concept to get into what we call the induction auto transformer concept. So here we can see that the entire power is transmitted conductively from source to load. So this is the source. So the entire power is like, you can calculate, this is 10 volt, this is 10 ohm resistance, then the current will be 1 ampere here, right? And here also, then how much will be the current here? The current here will be 10 by 5, 2 plus 5, 2 ampere. So 1 ampere is going here, 2 ampere is going here. It's clear for you. So useful power is the power which we have at the load, right? So the power will be IL square into RL, that is 2 square into 3, that is 12 volt. So 12 volt we are getting. But there is a lot amount of power that is getting wasted. The power going here is wasted, the power going, because the resistor is consuming those power. So the power wasted is 1 square, so 18 watts power is wasted, right? Only 12 watt you are getting, so around 18 watt power is getting wasted at the resistor. Because of the dissipation effect happening there, the power is getting wasted, 18 watt is getting wasted, and even under no load, because no load means this 2 ampere will not be there, right? No load means this will be open, so there will be no current here, only this 10 ampere will come. So here 10 watts is getting wasted. So lot of current is getting wasted. This is just a concept that you should keep in mind. This is the resistance potential divider. Okay. I'll make you understand why we are studying this. Okay. So here the input current I1 is equal to 10 ampere. Okay. We have a transformer here, 20 kVA single phase transformer here. And the input voltage is 200 volt, and it is being stepped down 2000, and it is being stepped down to 200 volt. Okay. Sorry, this should be drawn with a less number of turns. Okay. Then I1 will, how much will be I1? The kVA rating by voltage. So I1 will be 10 ampere, and normally you know step down transformer means the current in the secondary will be more, so it will be 100 ampere. So I1 will be 10 ampere and I2 will be 100 ampere. And you know input power is output plus loss, efficiency and all already studied. So input power is output plus loss. So losses will be copper loss and iron loss. So it will be just 1 to 2% because, take the key point, transformer has an efficiency of 98%. highly efficient machinery, because losses will account only to 1 to 2%. And you know the story of core losses, and you know the story of copper losses, and how you find out that everything you know. Okay. Also, in a transformer, V2 by V1 is equal to I1 by I2 is equal to K. So this K is the turn ratio in a transformer, and when it comes to the turns ratio in an auto transformer, we use another term. Don't get confused. Okay. So now we are at the auto transformer. So this is the setup of an auto transformer. This same transformer I am converting to the auto transformer. Okay, just keep that in mind. So this is the 200 volt secondary, and this is the 2000 volt primary. So here we are using a this is a tapping we are making, because I already told that part of the winding is common to both primary and secondary. So this was our primary and this was our secondary. But when it comes to the transformer, we don't say it like primary and secondary. Sorry, when it comes to the auto transformer, we don't say it like primary and secondary. This will be called as the common winding, because this is common to this side and this side. So we can say primary. Yeah, common means common to both the input side and the output side. Okay. And this will be the series winding. It will be in series with the load, so we call it the series winding. So it is series. It is in series with the output, right? So we have 2000 volt here, and this is 200 volt, and input current is, see how much is the input current? It will be 1, because here it was 10 ampere and here it was 100 ampere. Same calculation from here, and so input power will be 110 ampere. But you see the output voltage that we are getting is 200 into 1000 plus the resistance. So 2200 volt is the output we are getting here. See the difference. So the output is getting enhanced. So we know that KVA rating will be equal to V1. Common winding means common to both input and output. So KVA rating is equal to V1 into I1 is equal to V2 into I2. So V1 into I1, how much it is? 2000 into 110. So 110, you know how it came, 100 plus 10. So it is 220 kVA. Okay. And output also, how much it will be? This much voltage into 100 is the current coming here. So it will be 220 kVA. So both the input side and output side, so kVA will be same for a transformer, 220 kVA, right? So this is actually the kVA rating that we get in the, we know there are two processes, conduction and induction. So kVA rating in inductively means voltage across any winding. So here we took the voltage across this winding, the source side winding. So 2000 into current through the winding. Yeah, kVA means voltage into current, volt ampere, right? So that's clear here. So in our transformer, like the transformer which was here, this transformer, how much is the kVA rating? The kVA rating there is 2000 into 10, that is 20 kVA. Input kVA and output kVA. If we are calculating the transformer, here it will be 2000 into 20, and here it will be 200 into 100. Same value, like 20 kVA. Yeah. So in the transformer, we got the inductive rating as 20 kVA, whereas in the auto transformer, it is 220 kVA, right? Because why? Because in an auto transformer, we have both the inductive and conductive effect. Okay. So how much is the kVA that we got by conduction? We'll calculate, we'll subtract the total kVA minus the kVA that we got inductively. So 220 minus 20, that is 200 kVA is the kVA that we get through conduction. Conduction happens only in an auto transformer. So that's what the difference happening when we convert an auto transformer to an auto transformer, right? So always the high voltage, so some key points or tips what we can say, always the HV winding should be common, should be the common winding. You know, in the auto transformer, we have a common winding. So take the points, okay? We have a common winding and series winding. and the HV winding should be the common winding and the LV winding should be the series winding. Then only we get the benefit of boosting the value, because if we take it reverse, then it will be and also the polarity also is very important, where we keep the dot. The dot concept also is very important. So why we need an autotransformer? Because we get the boosted up voltage. So this is important for getting a boosted voltage. Okay. So coming in detail to what we call an autotransformer. In an autotransformer, I will make you familiar with the parts. So this is the voltage V1, and here so input voltage will be V1 and output voltage will be V2. So voltage, this is a series winding, right? So voltage in the series winding will be V1 minus V2, right? And the turns will also be N1 minus N2. So here I1 will be coming here, and here we will have I2. So here it will be I2 minus I1. This is clear from this figure. So how it is I2 minus I1? Why it is V1 minus V2? I think everything clear for you. This is N1, this is N2. So this much will be N1 minus N2. And this is V1, this is V2. So this will be V1 minus V2. This is I1 here, this is I2 here. So here what flows is I2 minus I1. So in terms of an autotransformer, in terms of an autotransformer, V2 minus V1 is equal to I1 minus I2 is equal to N2 minus N1 is equal to K dash. This is K dash autotransformer. And so we will conduct the KVA that we get inductively. So KVA we get by inductively will be, so here it's the induction effect happening here. So KVA inductively will be equal to V1 minus V2 into I1. So here V1 minus V2 into I1 is equal to, here the voltage is V2 into I2 minus I1. Anyhow, KVA rating is voltage into current. So we go for the source side and we go for the load side. So here the current is I1, whereas the voltage is V1 minus V2. So V1 minus V2 into I1 is equal to V2 into I2 minus I1. So this equal, yeah. And input KVA. So input KVA is V1 into I1 and is equal to V2 into I2. Input KVA. Input KVA is equal to output KVA. This is the KVA inductively. So KVA that we get inductively by KVA, input KVA will be V1 minus V2. So we are just substituting this we brought substitute here, and this is because it is in terms of I1, we took the primary side, I mean the series side equation. So V1 minus V2 into I1 by V1 by into I1 is equal to 1 minus V2 by V1 is equal to 1 minus K dash. So V2 by V1 is K dash. So KVA that we get inductively is equal to 1 minus K dash into KVA input, right? KVA inductively is equal to 1 minus K dash into KVA input. So you know KVA inductively why it is V1 minus V2 into I1 from the figure, V1 minus V2 into I1, and input KVA is V1 into I1. Already you know. Now we will find out the KVA conductively, how much KVA we get through conduction. So KVA conductively is equal to KVA input minus KVA inductively. So it will be 1 minus 1 minus K dash into KVA input, right? It will be 1 minus K dash into KVA input. 1 minus K dash, because from this equation, that's it. And we take common is equal to K dash into KVA input. This 1 and 1 and it will be K dash into KVA input. So this is a very important in term examination point of view. Now we will see for the same KVA rating. So we have a transformer, we have an autotransformer, and now we will see for the same KVA rating, converting a transformer to an autotransformer. So what is the difference in the core happening? So you know the core is made up of copper. So how much is the weight of the copper and how such difference is happening? So area of cross section of any conductor is, we will start. So this is the transformer. We have V1, which is V2, and this is I1 and this is I2. So we have the magnetic core, right? Sorry, I told you copper. So we know that the weight of the copper is proportional to volume, and so weight of anything is proportional to copper. So I am talking about the transformer. So weight of the copper is proportional to volume, and you know volume is equal to length into area. Volume is equal to length into area of cross section. You know that. So length we can write as number of turns into mean length per turn. So mean length per turn into number of turns will be the total length, and area is like area of cross section of any conductor is decided by the current passing through it. You have been studying this from the earlier classes, because resistance is equal to rho L by A. So depending upon the cross section, the current will also be more or less. So area we can substitute as M. So finally it will be equal to N into I. So this N into I is familiar for you. In the first class I have taught you some equations for MMF, that is the magnetomotive force. So MMF is equal to N into I. So we have this concept here. So weight of the copper is proportional to, should not write equal to, it is proportional to only. So weight of the copper is proportional to N into I, that is the MMF. Okay. So weight of the copper in a two-winding transformer. So what is a two-winding transformer? Two-winding is our common primary winding, secondary winding. That is a two-winding. So weight of the copper in a two-winding transformer is proportional to N1 I1 plus N2 I2, primary and secondary. That is the equation 1. And weight of the copper in an autotransformer. So you know the autotransformer here. In case of an autotransformer, this is the case here. N1 minus N2 is there and N2 is there. So in an autotransformer, it will be like N1 minus N2 into I1 plus N2 into I2 minus I1. From this figure, N2 into I2 minus I1 plus N1 minus N2 into I1, both sides. Okay. Serious side and the common side. Okay. And now we will take the ratio. Weight of the copper in the autotransformer. Why? Weight of the copper in the two winding is just cross multiply and substitute here. N1 I1 minus N2 I2. Yeah, you will substitute it here. And we know that the primary MMF is equal to secondary MMF. N1 I1 is equal to N2 I2. You know that. So that also we will substitute here. So substituting N1 I1 is equal to N2 I2 here, we get the weight of the copper in the autotransformer by weight of the copper in two winding is equal to 2 into N1 I1 minus 2 into N2 I1 by 2 into N1 I1. Okay. So again resubstituting, we get 1 minus N2 by N1 is equal to 1 minus K dash. So weight of the copper in the autotransformer is equal to 1 minus K dash into weight of the copper in the two windings. So two winding is our single phase transformer. So this derivation is very, very important. So only if you understand from the base what is a transformer, why it is I2 minus I1, V2 minus I1, all these things you should write, and finally you should reach this conclusion. So it's better you draw the diagram of an autotransformer also. It was there in my previous figure, that's why I didn't do this diagram. Also you should draw when you derive the amount of copper. This equation, when you derive this equation, you should it's advisable that you draw the diagram of the autotransformer also. So weight of the copper in autotransformer is equal to 1 minus K dash to weight of the copper into two winding, weight of the copper in the two winding transformer. Okay. Okay, so I hope the concept of autotransformer is clear for you, and how the kVA rating is get enhanced because of the conduction and induction effect both. So I think everything is clear for you. So this completes our study on transformer and autotransformer and everything. And next class we will be going ahead with the numerical problems, and after that we will move on to the induction machine. Okay, thank you.